Myself Rakhi, Assistant Professor in the Department of Electronics and Communication Engineering in ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Optical Communication, KC 058, I am going to discuss before you intramodal dispersion and intermodal dispersion. I already discussed about the dispersion in the last lecture. The dispersion, what does it mean? Again, just a recap of the dispersion what we have done in the last class. Dispersion, what does it leads to? Dispersion is a type of attenuation which leads to broadening of the pulse. Which leads to broadening of the pulse such that we can't able to distinguish between two adjacent pulse. And this one is called as the intersymbol interference or ISI. This is the basic definition or the basic description of the dispersion, that dispersion is a short of form of attenuation which occurs in the optical fiber during the transmission process, and it leads to the broadening of the pulse from the input to the output end, and such that we can't able to distinguish between two adjacent pulse, and this phenomenon is known as intersymbol interference or ISI. So, this dispersion has got two types broadly. First one is called the intramodal dispersion, the second one is the intermodal dispersion. In the intramodal dispersion is further divided into material dispersion and the waveguide dispersion. These are the two types of intramodal dispersion. So, in this particular lecture, I am going to discuss before you intramodal dispersion is two types, that is material dispersion and the waveguide dispersion, and a slight description of the intermodal dispersion. In the next lecture, we will go through detail about the intermodal dispersion, in which we will go see the intermodal dispersion in the multimode step index fiber, intermodal dispersion in the gradient index fiber, and so on. Now, just the introduction of the intramodal dispersion. Intramodal dispersion is also called as the chromatic dispersion, as I have already told about this to your previous class also, in which we have discussed about the dispersion, that intramodal dispersion is called as the chromatic dispersion. In occur in all types of optical fiber. There is a restriction to the dispersion in the fibers also, because when we talk about the intermodal dispersion does not occur in the single mode, it only occurs in the multi-modes. But this particular intramodal dispersion occurs in all types of fibers, and types of fibers is already known to you. What are they? They are multi-mode gradient index fiber, multi-mode step index fiber, and the single mode step index fiber. These are the two major types of fibers, and this chromatic or intermodal dispersion occur in all these three types of fiber due to result from the finite spectral line width of the optical source. So, which factor is responsible for this dispersion is the optical source, and two types of optical sources broadly known to us, that is LED and the laser. So, we have to always keep this in mind, that this intramodal dispersion occurs due to the optical sources finite spectral line width. So, whatever light is emitting, whatever signals are emitted from the optical source, which led to the intramodal dispersion, and if we want to have a control over, so first of all we have to choose that type of source which have a narrow which have a control over the finite spectral line width. We have to keep control over the finite spectral line width, and we have to choose our source accordingly. Since optical sources do not emit just a single frequency, but it emit a band of frequency, then there is a propagation delay difference between the different spectral component of the transmitted signal. What does it mean? That normally any type of optical sources does not emit a single frequency of light, and it emit a multiple band of frequency. So, there exists always a propagation delay. As we know, frequency is equal to C by what? C by lambda, where lambda is our wavelength and C is the velocity. So, if there is a different frequency, then of course velocity changes as per that. If we have a signals of different frequency, velocity changes as per that, and of course as per that we have a delay difference, because distance is also related to velocity. In general terms also, and in communication also, it is related to velocity, is related to time, and distance is related to velocity. So, delay difference is also related to our velocity and the in turn to the frequency. This causes broadening of each transmitted mode, and hence it is called as the intramodal dispersion. And whenever there is a broadening due to this, then it is called as the intramodal dispersion. So, dispersion delay difference may be caused by the dispersive property of the waveguide material, that is material which are used have got some dispersive property, and if delay difference is caused by that one, then it is called as the material dispersion. And if delay difference is caused by the guidance effect within the fiber, within the optical fiber more precisely, then that is called the waveguide dispersion. Again, just a recap, that intramodal dispersion is also called as the chromatic dispersion, and it occurs in all type of fiber, and it results due to finite spectral line width of the optical source. So, optical source is responsible for that. So, we have to choose the optical source as per the its by seeing its finite spectral line width. Since optical sources does not emit a single frequency of light, it emits a band of frequency. So, there exists a propagation delay difference between the different components of the transmitted signal. That means, different component at different frequencies of the transmitted signal, and this causes the broadening of each of the transmitted mode, and hence it is called as the broadening. Whenever broadening occurs, then this is a dispersion. It has got two types. First one is the material dispersion, and the second one is the waveguide dispersion. Now, material dispersion. Pulse broadening due to material dispersion result from the different group velocity of the various spectral component launched into the fiber from the optical source. So, dispersion which occurs due to pulse broadening. So, whenever we call about the dispersion, we are talking about the actually pulse broadening. That is why the statement start with the pulse broadening. So, what we can say dispersion or we can say pulse broadening, it means the same thing, because dispersion is always described in the terms of pulse broadening. So, pulse broadening occur in the due to material dispersion result from the different group velocity of various spectral component launched into the fiber. Different group velocity, if a component of light, the light launched into the fiber has got a different component, different spectral component, and this group velocity of all that is different, that leads to the pulse broadening due to material dispersion. It occurs when the phase velocity of a plane wave propagating a dielectric medium varies non-linearly with the wavelength. So, again there is a condition arises that phase velocity of the plane wave propagating inside the dielectric medium varies non-linear with the wavelength. And about the non-linearity and the linearity conditions we have already discussed in the previous lectures. And again one more condition, a material is said to be exhibit material dispersion when the second differentiation of the refractive index with respect to wavelength is not 0. That means, what is the refractive index here? Refractive index is given by this term and second differentiation, that means d square n with respect to wavelength should not be equal to 0. So, whenever any equations comes with respect of material dispersion, this condition is always applicable. Now, just have a knowledge about the pulse broadening, ki how much the broadening is taking place due to material dispersion, what will the value of broadening, that is what is the value of dispersion, because dispersion parameter can be measured with the help of pulse broadening only. So, we are going to discuss it for the material dispersion, and this is a very important topic which you have to study it carefully. Now, pulse spread due to material dispersion may be obtained by considering the group delay. Group delay, we can calculate the pulse spread due to material dispersion with the help of group delay in the optical fiber, which is a reciprocal of the group velocity. So, whenever we got the group delay tau g should be reciprocal of the group velocity v g, and we know v g is equal to del omega by del beta. That is why here tau g we can write it 1 by v g is equal to 1 upon del omega upon del beta. So, we will get this equation up of d beta upon d omega. Now, in the next step what we are going to have? Beta is normally written as 2 pi by lambda, already known to us, that is the propagation constant. Beta can be written as 2 pi upon lambda, where lambda is the wavelength of the signal transmitted. But if we write beta with respect to certain refractive index, then we have to multiply. If we write it with certain refractive index, for example n1, which is the refractive index of the core of the optical fiber, then it changes into n1 2 pi upon lambda. So, we will substitute this value of beta, that is n1 2 pi by lambda here, and also omega is equal to 2 pi f, but we can write f in what way? F is our frequency, and frequency can be written as c by lambda. So, we can substitute here also the value of omega 2 pi c upon lambda, and upon differentiating it we will get this value, where c is the velocity of light, n1 is the refractive index of the core through which signals are propagating in the optical fiber communication, n1 again your core refractive index, and lambda is the wavelength of the signal propagating inside a waveguide, that is our optical fiber. Now, the pulse delay tau m. Now, this is a general description of a general formula of a group delay. Now, we are moving towards the particularly of the material dispersion, and it can be written as tau m. So, if we want to write the pulse delay tau m due to material dispersion for the fiber length of L, then we have to just multiply. Tau m can be calculated for a length L by just multiplying L with the tau g, that is our group delay, and you can easily see what is difference between this expression and this expression, only numerator L. So, just we have multiplied L here. so as to get the tau m, that is pulse delay tau m due to material dispersion for the fiber length of L. Now, this is the group pulse delay. Now we are taking a source are responsible for the this one intramodal dispersion, or we can say material dispersion. So, if we have taken a source of RMS pulse width sigma lambda, subscript में lambda and the sigma, which is the RMS pulse width. With a mean wavelength lambda, the RMS pulse broadening due to material dispersion sigma m may be obtained from the expansion of the Taylor series about lambda. We have to expand it with the expand in the Taylor series with respect to lambda. So, what we get after that? Sigma m, that is pulse broadening due to material dispersion. Sigma m is the pulse broadening due to material dispersion, and sigma lambda is the RMS spectral width of a source. So, do not be get confused between the sigma and the sigma lambda. Sigma lambda is the RMS pulse width of a source, and sigma m is the RMS pulse broadening due to material dispersion. Now, we have sigma, we have employed the Taylor series with respect to lambda in the sigma m. So, what we are getting? RMS spectral width of the source and differentiation of tau m, that is our pulse delay with respect to lambda. We keeps on doing this. This is the extension of the Taylor in the form of a Taylor series, but as the first term usually dominates, especially for source operating over the range of 0.8 to 0.9. So, we have taken a special condition for a source operating over 0.8 to 0.9 micrometer wavelength. So, we have taken only the first term from here and discarded the other term, higher order term. So, we will get this one sigma m, that is our RMS pulse broadening due to material dispersion, is equal to sigma lambda, which is our RMS pulse spectral line width, tau m group delay due to material dispersion, d lambda yani wavelength. Hence, the pulse spread may be evaluated by considering dependence of tau m on n. Of course, tau m is dependent upon lambda. So, for calculating the pulse width, we have to just calculate this one. For calculating this, we have to take the differentiate tau m with respect to lambda. So, where is our tau m? Tau m is our this one. We have to differentiate this with respect to lambda. So, what we have to do? We have to d upon d lambda, and what is the value? L by C n1 minus lambda d n1 upon d lambda. L by C n1 So, we have to differentiate it with respect to lambda. So, what we are going to have? We will get this. We will get this. But after differentiation, this value and this value get cancelled out. So, at last we will with this only this and this one minus L by lambda upon C d square n1 upon d lambda square. And now, we are going to substitute d tau m upon, that is our due to material dispersion d lambda, that here in this expression of A, we will get the value like this. Just different putting the value sigma lambda, and we have L by C lambda d square n1 upon d lambda. So, when we substitute the value, we get this as, And now one of the important parameter or can also be derived from this, that is our material dispersion parameter, which is given by m, and it is equal to 1 by L d tau m upon d lambda. So, again we have to differentiate tau m, which is here, and put it here, they will get this, which is often expressed in the form of picosecond, nanometer inverse and kilometer inverse. Now, I am going to have discussion with you one of the numerical based on this. What does the numerical say? A glass fiber exhibit material dispersion given by this. So, as already told to you that in every equation, in every expression where the material dispersion are involved, double differentiation of refractive index with respect to wavelength can't be equal to 0. That is why here the condition is given here, what lambda square d square n1 upon d lambda square is of value 0.025. It can't never be 0. Determine the material dispersion parameter, that means you have to determine m. M is our material dispersion parameter at a wavelength of 0.85 microsecond. What the wavelength has to be taken? 0.85 microsecond, and estimate the RMS pulse broadening per kilometer. And you have to first find out the material dispersion parameter, and after that you have to find out the pulse broadening per kilometer for a good LED source. It has taken a LED source having a spectral line width of 20 nanometer at this particular wavelength of 0.85 micrometer. So, we are going to have the value of, calculate the value of m and sigma m, and already we have formula of this and we are going to substitute that. Now, using the formula of dispersion parameter. So, dispersion parameter is given by m is equal to lambda by c d square n1 upon d lambda square. But do we have a value of this d square n1 upon d lambda square? We do not have a value of this. We have a value of lambda square d square n1 upon d lambda square. We have a value of this as per the question. Lambda square d square n1 upon d lambda square, we have the value of this, and this is equal to 0.025, but we want this value. So, just what we have to change, make a change, we have to make a change in this case as lambda by c d square n1 upon d lambda square. We should multiply lambda in the numerator and also in the denominator. So, when we multiply lambda in numerator as well as in the denominator, what will going to happen? Lambda square multiplication both in the numerator as well in the denominator. So, lambda square numerator, lambda square denominator, lambda here also, from this lambda by c, lambda square denominator, lambda square in numerator, d square n1 upon d lambda square. So, what will be the value of m we are getting? 1 by c lambda, lambda square d square n1 upon d lambda square. Now, here comes it is, and we have the value of this, the value of c lambda, substituting we will get the material dispersion parameter. Now, we have to calculate the pulse broadening. Pulse broadening is given by this expression. So, we have a value of sigma lambda, that is our spectral line width of 20 nanometer. We have the value of per kilometer, that means L should be equal to 1. We have to first find out the value of this. If we want to relate it with the help of with the m, what is the change? sigma m can be written as we have already calculated the value of m. So, just I want to write sigma m value in the terms of m, sigma lambda L, take it as common, and if we take this lambda outside the bracket, that is lambda by C. And now you can see that this expression and this expressions are same. So, we can write sigma lambda L m. So, our pulse broadening due to material dispersion can be changed as sigma lambda L m, and all values are available with us. On putting that, we get this one. This is our pulse broadening per kilometer. That is why L is taken as 1 here. Now comes the waveguide dispersion. Waveguide is a second form of intramodal dispersion. The waveguiding of the fiber may also create chromatic dispersion, that is our intramodal dispersion. The result from the variation in the group velocity with wavelength for a particular mode. Considering the ray theory approach, it is equivalent to the angle between the ray of the fiber axis varying with the wavelength, which subsequently relates to the variation in the transmittance times of the rays and hence dispersion. What is saying in this line? Angle between the ray and the fiber axis varying with the wavelength. Already known to us that velocity varies with refractive index. This is already known to us that velocity varies with the as we change the refractive index, our velocity changes, and also wavelength is dependent upon velocity. All these parameters which are considered in the fiber are related to each other. So, there is an angle. What is the fiber axis and at what angle it is incident keeps on varying with the wavelength, with the our lambda, and due to this all the rays reaching at the destination are with different group velocity, and that leads to the dispersion known as the waveguiding dispersion. And as it is comes under the category of what? Intramodal dispersion. So, this condition is also applicable for this one also. For a single mode whose propagation constant is beta, the fiber exhibit waveguide dispersion, and it has to follow this condition, which is a condition for the intramodal dispersion. Multimode fiber, where the majority of modes propagate far from the cutoff, are almost free of the waveguide. So, in the what about with this particular dispersion is not exactly, it is either it is negligible or it tends to 0 for the multimode fiber. It is most prominent in the case of a single mode fiber. However, with a single mode fiber where the effect of different dispersion mechanism are not easy to separate, waveguide dispersion is significant. Now comes the intermodal dispersion. About the detailing of the intermodal dispersion, we will consider in the next lecture. Today, in this particular, just an introduction about the intermodal dispersion. Pulse broadening due to intermodal dispersion results from the propagation delay, difference between the modes, different modes within the multimode fiber. At the different mode which constitute a pulse in a multimode fiber channel different group velocity, the pulse width at the output is dependent upon the transmission line of the slowest and the fastest mode. As we know, we have discussed about the different types of rays. First one is the axial, skew and the meridional. Axial ray is the fastest ray and the meridional ray is the slowest one due to the path travelled by the different rays, and due to this ray difference at the destination when this rays enter, then they have a different timing. So, due to this dispersion exactly occurs due to, and all the rays travels within the optical fiber. So, we will go through the detailing about the intermodal dispersion in the next lecture, which comprises of the intermodal dispersion and its propagation in the multimode and spread index fiber and the multimode step index fiber, because intermodal dispersion does not occur in the single mode fiber. Single mode operation, there is no intermodal dispersion. So, thank you for attending today's lecture. We will meet again to discuss the intermodal dispersion in detail in the next lecture. Thank you.